All right, let's hope this stream goes pretty decent. For those of you who, it's kind of early on, there's like no one here, but if anybody is watching the stream, we're mostly going to be just talking about how to actually build the software for the multi-threading platform and pretty much just go over a little bit of other nuances like bug fixes and stuff that I did. I've been pretty busy this week, so I haven't really gotten a chance to put out videos, so this is the main video for Friday. So I'm just going to wait until people start coming in and we'll just go from there. So there will be once the stream ends, for those of you who are watching this later on, there is going to be a link in the body description. So if you want to skip to the starting point of the video, then you can, just skip there. So that way you don't have to wait until everyone kind of gets in. But yeah, so I'm gonna just do this. I forget I can put this on the second screen. Nice. To make it a little easier. Cool, cool. That took 16 seconds and it didn't even compile it. That's weird. This is so stupid. Holy, are you serious? Oh, that is right. Okay, that sucks. Hmm. Local jump. I see, like, looks like somebody's bouncing in and out. I'm just waiting for more people to come, but if you have any questions, you could always just put it in the chat. I can like answer it and stuff. So right now I'm just mostly just working on the just-in-time compiler. I've been up to quite a lot of stuff since like, because I know I haven't been posting that much, but I've actually been doing a lot to the language to like make it better. Um, I would like to do another stream dedicated to probably the just-in-time compiler. I guess we could talk about it in the stream because you kind of need to with the multi-threading platform, but yeah, that can probably be another stream. But been doing that and like tons of other like side projects with the language as well. So it's been pretty interesting. I remember there being a jump if equal to. Oh, I guess so. Nice. Isn't this the same thing? It's weird. It keeps saying like I'm dropping viewers. If you have, like I said, any questions or just wanted to say hi and let me know you're like watching the stream, then I guess I can just start talking about a bunch of random stuff. Um, just let me know in the chat. Otherwise, I'm just gonna keep working on the JIT. That was easy. Yeah. Oh fuck. I'm probably just gonna wait a few more minutes because like this recording is recorded. So if anybody's watching the video, they can just like watch it later if they don't show up. So I'm probably gonna give it like 5 more minutes at the most. Oh, nice. So this is an example like right here of the JIT. So basically what ends up happening is the JIT works 90% of the time. There's still lots of stupid bugs that I haven't figured out yet that I've been like tirelessly trying to fix for the past, I don't even know how long I've been working on this, but so I have like this sample program that basically loops. So you can ignore this stuff. That's other stuff I was doing, but you can basically loop, and this kind of ties into the coroutine system. So you basically loop for like 10 million times. Now, if I put the flag in here to the virtual machine and say no JIT, that's going to do is that's going to tell the system to not run the just-in-time compiler, and it basically it basically just runs all this at the high level. So at the high level, meaning that, and I use that term loosely, the high level means right here. So in the system, and we're going to see this in a second, but like as we go through like all the code for the coroutine system, we can see that basically we have what's called the high level, and then we have what's called the low level. The low level is basically the actual low level instructions that gets translated from the high level. Now, the only way that I've been able to achieve being able to execute 100,000 coroutines per second, I can do it at the high level. I mean, I talked about it last week. I think it was like Sunday when I did the video, where I could basically run, I think, what was it, like 100,000 in 20 seconds or something like that? Yeah, I think I said 20 seconds. um, 20 or 21 seconds. But now I basically got it down to, I think, like 5 seconds or something. And I'm trying to get it faster. Ideally, it should take a second to execute. So with the just-in-time compiler, it's slightly sped it up, but because it has so many bugs, I'm throttling a lot of the performance because it's just not ready yet. But you can see here in this example, like the benefits of running the just-in-time compiler. It took 20 seconds to execute the program. And again, the just-in-time compiler is not, it's not really optimized, so it's super slow, but it basically executed all this source code at the high level, which means every time when it tries to execute an instruction, it has to decode all this information. So it has to figure out, you know, what are like the parameters for each instruction. So like for imod, you know, what register are we trying to access, what register are we trying to read data from and then write data to. Um, and yeah, so it does that basically every instruction, and it's very inefficient. So you can see here it took like 16. But if I remove the no JIT flag, it's going to take a lot less time. Now, it's going to call it first a couple times before it actually executes it. So you see it took like 3 seconds from like 16. Um, the system has to figure out that this is what's called a hot function. Hot functions are basically functions that are defined as something that you call a crap ton of times. So right now, if you call this, I think 25,000 times, then it's going to be considered a hot function. I'm actually going to change that right now because it's a little bit too high. So if I go to, I don't remember where that was. I think it's in method.h. So there's a concept of a JIT-IR limit. Yeah, here it is. So I'm going to put it to 15. And if I execute 15,000 instructions on a single function, and an instruction includes calling the function, it includes for loops, if statements, so on and so forth. Any instruction that executes in there, once there are 15,000 instructions executed in that function over the course of its lifetime, then it will convert it to the JIT. Because even if you're not doing something like, for instance, in this example, if I go back to this one right here, in this example, even though I'm looping, you might have a simple function that, I don't know, does something very simple, like getting the size of an object. So like this coroutine builder has a list that manages all the current running coroutines. So if I go to like synced lists, which is a API that the language uses, to create all these coroutines. There's a size function in here somewhere. So if I do a search for size, it basically just locks the current instance and then returns the number of elements. So this basically just reads this variable up here. And yeah, so it's a very simple function, but it usually takes quite a bit of time to do this at the high level because you have to set up the function and then you have to call it immediately. And you still have to do that at the high level as well, or at the low level. But the only difference is that you don't have to execute all of these boilerplate like source code. So like there's a lot of stuff in here for checking whether or not we have a signal. We also check to see whether or not we need to context switch. This is going to be something that we're going to see in a little bit on how it actually works. And then there's also like every time we branch, it's incrementing the program counter and then like jumping to the next instruction, which just might be literally right below it. So we can actually see an example of how the GIT works. So if I go to call, and this is what we call a function. Now this code here, what this does is every time when we execute a method, there's a potential that when we try to execute a certain method in the programming language, and we've gone over this function before, it basically just sets up the stack and then tries to figure out whether or not we should JIT the function. When this actually gets called, there's a chance that it could potentially return a just-in-time compiled function. Oh, I got some boilerplate code here that shouldn't be there. Yeah, so there's a chance that like this could actually be returned, which represents the function pointer of the just-in-time compiled function that was compiled at runtime. So I'm gonna just try to see if this works. Hopefully it doesn't crash on me. But then once we see this, then I'll start like talking about like all the components that you need to build a coroutine system in your language. And then we'll just kind of build on it from there, basically. I freaking lost my web page. Sorry, I'm like on a different screen trying to look up something to kind of help explain this. There was a website. I'm going to see if I can try to find it while this is taking a really long time. It usually doesn't take this long to build. I'm going to see if I can try to find a website where I actually first started learning about coroutines. And this kind of started the journey of me like trying to implement coroutines in my programming language because I think it's pretty cool to be able to have a truly concurrent language. So we'll see that in a second. Did it freeze? What's going on? Common coroutines. Hopefully it's running right now. Hopefully, yeah, I just compiled it. Okay. So you see that this is debug information that I'm getting printed out from my just-in-time compiler. So the just-in-time compiler compiled the loop function, which is, if I go back to the code, so it compiled this loop function, which has this for loop in it. And it says this is the size of the function. So one thing you want to pay attention to when it comes to like building all of this stuff, the just-in-time compiler and the coroutine system, you need to pay attention to size. That's going to be like the theme of this video. Memory matters because if you're not careful, you can actually, when it comes to scaling it, it becomes unbearable. So like right now, you can see this loop function took about a little over 1600 kilobytes. So 1.6 kilobytes basically. And like that may not seem like a lot, right? Like 1000 bytes, 1600 bytes is not that big. But when you scale this up to compiling, like let's say I had, I don't know, 10,000 other loop functions that had the exact same code and or similar amount of code that basically ended up outputting the same amount of size. So let's see. So because I'm bad at math, this is like super embarrassing. If you do 1600 and then times, what did I say, 10,000? I'm bad at math and I have a bad memory. That's going to be, let's see, 160 megs. So basically for every 10,000 of these functions, you're going to, is that right? 1, 2, 3, 4, 16, 1, 2, 3. Yeah, that's okay. So if you do that times 10,000, that should be, yeah, I thought that was a bit much. That should be about 16 megs. Yeah. So basically for every 10,000 functions of loop, you'll allocate 16 megs, which now that actually becomes a pretty decent amount of memory. And then again, if you scale up to 100,000, now will you have 160 megs. So it quickly becomes a pretty big deal when it comes to scaling upwards for each function. Now, the reason why it's 1600 megs is because functions have a lot of overhead. This is another thing you want to think of when it comes to building your coroutine system. The overhead is very important because you want to make sure that it's as minimal as possible, because otherwise you're just going to have a headache like trying to build it. Uh, YouTube is not receiving enough video to maintain streaming. What? YouTube is not receiving. Why is it? Oh crap! I'm having the same. Am I having the same Wi-Fi issues I did last time? This sucks. Let me see if I can fix this. This is like so stupid. So I'm raising the bit rate. I don't know if that's supposed to be better. My guess is more bits means higher quality. I'm not a video engineer, so I don't really know how this stuff works. Hopefully that fixes it. Alright, maybe if I disable DVR, then that'll make it a bit easier. Unless replay one streams. Copy, copy, copy. And refresh the page. I don't know, could somebody like put in the chat whether or not it's actually working? Like if you can actually see anything, because I don't know what the heck's going on. It's saying that it's not receiving enough video to maintain smooth streaming. Like I don't really know what I can actually do about this. Seems like the stream's health like dies after a certain amount of time. Okay. Well, hopefully it's not too bad. If it's too difficult, then just let me know in the chat. I'll maybe try to do something, but I'm just gonna keep going on. Um, you can replay this, so hopefully it shouldn't be that much of an issue. This is still going. Why is it still going? Oh, okay. I remember. I lost track of what I was even doing. Okay, so now we're going to go into the actual source code here. And we're going to see some of this overhead in the actual function. So we're about to call the JIT function, which takes a JIT context. The JIT context is going to be the most minimal, the bare minimum amount of information that we need to basically execute a JIT function. And you want this to be very minimal. You don't want this to be too much, because then it's just going to make it very difficult to actually process the information, because this information is like basically known as volatile information. What that means is basically once you call the function and you pass it this JIT context, you need to take all this data and rip it off of that object immediately, because once you call into another function, all of this data could be completely different, because we're going to reset the data again once we call a new function. So that's part of the overhead, and we're going to see a little bit more of the overhead in a second. So if we go back to the function, if I hit this little red button here, this actually forces us to step into the source code. You don't want this one, because then you won't actually see the execution. So if you hit the red button, that's going to force us in. Now, the debugger is going to freak out a little bit because it doesn't know what's going on. This is a dynamically allocated function, so if I just force step into it one more time, it's going to bring us into the frame of the actual source code. Now, this is source code that I generated as a result of the programming language. So I'm going to drag this. Where's the actual tab at? I don't even know where the tab is. Oh, here it is. So I'm going to drag this over to the left, and over to the right, I'm going to open up the base assembler, and then the assembler, and then finally the assembler.h. I'm going to take all these and put these right here. So there's several sections. Now, there's been a lot of changes to the actual JIT, and I'm not going to spend too much time on this because this is really about the concurrency system. But basically, once we compile it, as you guys know, I had this little example a couple of videos ago where I talked about how to build a JIT. All this stuff, for the most part, still stands. We basically pass it a JIT context. We check to see if the caller, the function that we're trying to call, we check the JIT labels, and we check the index of 0. If that's equal to 0, then we go to the label table, which then updates any labels. So if we try to bounce around in the function, we know every spot that we need to bounce around in to make that work. And then we also have the thread check section. I've added a couple more sections to this, and I'm just going to skim through this because I don't want to spend too much time on it. But basically, if I go back to the disassembly, where's the debug thing at? There we go. Okay, so the disassembly is going to start here. So when we actually compile it, and again, this is where it comes to thinking about the overhead. And if you guys have any questions about this, you can put in the comment section below after the video is aired, or if you guys join during the stream, you can always do that as well. We create what's called a function prologue. This is considered the prologue. The prologue represents basically all the source code that we need to execute to set everything up. So I'm just gonna skip over this. This basically just sets up the stack so that way my system doesn't crash. It's not gonna crash your computer, because even though this is machine instructions running on the CPU, you do want to be careful, but there's not anything here that's going to break it. It'll just crash the entire application instead of my computer. And then this section basically sets up or allocates the stack space. So what this is doing is we're basically just setting up any local variables that we have on the stack. I have several local variables at the low level on the stack that I use for multiple different things, which we'll get into later on. So I'm going to skip over that. The next section is setting up the stack and the register values. So this part right here sets up the stack and the register values. Now the way that I've done this, and I'll mention this very quick, it's a very good way how I've done it. This basically allows for me to abstract away from all of how the interpretation of the system works. This is something you want to do when you're actually, oh, is my laptop about to die? Crap. Seconds. All right. So basically, you want to do it this way because it makes it a little easier to like process stuff. So we have what you're going to want to do is create a base assembler. This is going to be the base level of how your GIT is going to work. Then you want to create an x64 assembler. This is going to have the implementation of all of the functions that you're forcing to implement in the base assembler. And the x64 assembler is going to inherit the base assembler, obviously. And that's going to override all those methods that we need, so that way we can obfuscate away how things happen. All we want to say is in the base assembler, I want to do a thing. I want to set up the stack and register values. But we don't want to care about how this works because eventually I'm going to be supporting ARM processors, MIPS processors, and more with this GIT system. So if I just say set up stack register values, then I can create an indefinite amount of these classes and just override these functions and then just do whatever I need to do based on that processor. So that's a little bit of a little tidbit of what I wanted to mention, but yeah. So if we keep going on, and you can kind of see, this is kind of why we have overhead. Like none of this code is as a result of like the user code. So like I wrote the for loop here. We haven't even gotten to this source code yet. We're about to get there. So the next thing after we set up the stack and register values, we need to set up the address table. Now I don't remember what that did, so let me set up address table. Oh, okay. And you notice I'm skipping some functions like create function landmarks. That's a function. I skipped over this one because all it does is just creates a bunch of like labels. And these are basically just points inside of the actual GIT function where we can bounce around. Like, there's a point in the function where the actual code starts. There's a point in the function where the opcode actually starts executing. So there's two parts. There's the part where the code starts, and just before I start executing the opcodes, we're going to see it in a second, but I basically try to see where we need to jump to. There's also, stuff at the stack and a bunch of other crap. So we want to do all that, but then the address table, if I copy that, do a search for it. Oh, okay. So what this does is this does this code right here. So you can see this assembly code here represents the if statement that I just talked about, and it says go to setup addresses. So we basically just pull the data down from the function and then the JIT labels value, and then yeah, we just make sure that it's null. And if it's null or if it's equal to 0, we set up the address table. Otherwise, we go to the stack check section. So I'm going to skip over all this. Now it's going to jump to the label table because obviously it's the first time we initialize the function. So it's going to initialize all the labels for all the instructions. These are various different points in the actual function that we can execute. So now it bounces back up to where we were, and now it's in what's called the virtual stack section. So we call validate virtual stack. Yeah. So immediately after we set up the address table, we validate the virtual stack. Now what this does is this is where we start getting into the coroutine system. So I'm going to back up a little bit because this is really low level after we kind of go over this. But basically, coroutines, the way they work is you want to rebuild the stack once you execute a coroutine. So just put that in your head. I will talk about that in a second. But basically, this code checks to see if we're rebuilding the stack. So I access the thread object, the thread pointer, which is a pointer to the actual value in the JIT context. And then I access the stack rebuild local variable, which is basically just a Boolean value that says whether or not we're rebuilding the stack on this thread. If that's the case, then we call a function called shift to next method. And then after that, we basically get the current program counter, and then we jump to that specific label. So we'll see that a little bit more, but yeah, so I'm just going to execute all that stuff. And now I have some debug stuff. So I have printouts here that show each instruction. Let's see. Is that? Yeah, here it is. So if I put this right here, then I go back to the execution. I'm going to jump down. All right, so now we're at the user code. So we've already validated the virtual stack. We're not rebuilding the stack at this point because we didn't context switch. But we're basically ready to execute all these instructions, and you can see each instruction has an address value. 0x3, 0x5, 6, whatever. So we're at 0x0, which is the first instruction. We execute iStore local, and then we execute 0x2, which is right here, which is load local, and then so on. So 0x3. You can see like the amount of instructions that it takes to do this. 0x, what is this? 5. Less than. Each instruction or in the actual programming language differs in size, right? So you see 0x3, which is the move I, is a very short instruction, whereas checking to see if two registers in the programming language are less than each other, it's quite a bit more. It's like, what is that, 3 times the size of that actual instruction. So this is another thing you want to keep in mind when it comes to building your virtual machine, because the more instructions you execute, the worse it's going to be. All right, so now we're down here at this instruction, and here's how the label system works. So we're going to jump to 12, which is down here. Now we're going to say jump not equal to. So as long as we're less than 10 million, then we're going to jump back up to the top. So if I do this, execute this, and it's going to actually physically have the address of where we need to jump to. So it's going to jump. Oh, that's weird. Oh, okay, 12 is the end. Okay, and then it jumps back up to 2. Okay, so what it's doing is we're saying if we're greater than this value, then, or if we're not less than this value, then we jump to the end. Otherwise, we increase the index of the local variable of 1, and then we jump back up to the top. So it's just 2 jump instructions. So we execute 0x9, and then finally, we execute the jump instruction, which then jumps us back up to 0x2. So now we're back up to here. So we're going to keep doing that indefinitely. I'm not going to go through it because it is 10 million times. But I just wanted to show you kind of, how things work in general. And then if I scroll down here, because there's a lot more overhead. So this section right here is known as the thread, or actually no, it's the stack check section. Whoops. So there's multiple sections in here. I'm just going to go back here because it's a lot easier. So I have a stack check section. You're going to want to implement a dynamic stack allocation system, which we'll go over in a second. You also want to have a thread signal check, which is the thread check section, which is right here. You can see I'm checking to see if whether or not we need to suspend ourselves within inside of the JIT function. We're going to need to do this in case there was a garbage collection, and the garbage collector needs to suspend all threads. So we call thread suspend self. We also try to catch exceptions as well. So this thread signal check section also handles exceptions in the programming language. And then finally, we try to context switch. So what is this? Store label values, and then function epilogue. Yeah, I don't know what this stuff is doing, but I'm pretty sure it's somewhere in there. Then finally, we have the label section, store label values down here. And then after that, we have the function epilogue, and then the constant section. Now, this function does not really use constants. I mean, it does, but not in the traditional sense. It doesn't have any like floating point constants. So there's nothing, this is just garbage afterwards. But as you can see here, we actually return inside of the function. So typically when we return inside of a function or out of a function at the high level, we would do everything in that same execute function. So I don't know where the actual tab is, but in the thread execute function, we would basically bounce around, and then once we call return, we would call this function here and then return out. Well, since this is at the low level, we want to do all of this work inside the function itself, and then restore the stack once we're finished with it, because obviously I screwed up the stack because I ended up calling this function. So I have to reset the value of what the stack is supposed to be at the end of it. And that's the entire flow of how it works at the low level. So now let's back up a little bit to kind of understand what is coroutines, and then how are we going to implement it in the programming language. So I had a tab. What the heck was that? Oh, here it is. Okay. Can I view the actual thing? Because it's on a website that requires a subscription. This isn't even the thing that I was looking for. So I can find a different one. Okay, all right, here it is. So I'm going to take this tab, put this right here. All right, so in order to understand, like before we start building the system, we have to first try to get a concept of what is a coroutine. So coroutines are basically a way for you to delegate work on a myriad of multiple different threads, um, without actually having to depend on a physical thread for execution. Meaning that if say I want to, I don't know, write data to a file, you can write data on thread number one, and then if that, at some point during writing to that file, that coroutine decides to go to sleep, it can then go to sleep and then run on thread two if it wants to at any point. So it's not really dependent on a specific physical operating system thread to do the work that it needs to do. So in this example, this is kind of cool. I'm going to put this in the chat, even though there's no one here. um, so here's an example of if you have a coffee shop, you can basically try to make coffee, right? So let's say you have a list of orders that you want to fulfill. And, in a traditional sense, what you do is you just fulfill all those orders in a for loop. This is very inefficient because basically you have to do everything what's called sequentially, meaning that, in order to, execute the second order, the first order has to be done first. And if, you can imagine, let's say you had a coffee shop, in this example, and let's say you had a Starbucks, right? And, they're working on 5 different orders. Well, if you have one person working on those 5 orders, well, that one person can only fulfill one order at a time, so it's a bit inefficient. But if you have, 2 people working on those 5 orders, well, now that work can be at the very least split in half. So now you have 2.5 orders per person, basically. Um, and it's kind of nice, but even still, you can run into issues where, what if, there's an order that's being blocked. So let's say we got 2 people, building the actual coffee, and the second person has already fulfilled one order, but the first person is still working on their very first order. And the second person needs to use the machine that the first person is using, to actually do anything, which that can then of course cause issues because now you're still basically executing it sequentially, in a sense. So if we scroll down here, we can kind of see how kind of coroutines work. So in a typical threading system, you'd have 5 threads, and they would just execute on a CPU. And the operating system would schedule all these threads sequentially. And you don't notice that because the operating system is context switching all of these threads at such a low level, and they're doing it so often that you don't really notice that all these things are happening at the low level. So if we look here now, let's see, we have a coroutine. So you have like basically one thread, and you can have all these individual coroutines that have their own time slices and are running at various different intervals. Like you can see this one is a very big time slice, then this one runs for a little bit, this one runs for an even smaller one, then this one runs again, and then it just keeps flip-flopping back and forth between various different coroutines. And coroutines, you can think of them as basically lightweight threads. A lightweight thread is basically just a thread that, it's a green thread, right? It doesn't depend on a physical resource to operate. Um, I like to kind of think of it as, a car. So if you have a car, you need the thread is the ability to do the work. And so, you have like the car, you have the wheels, you have the transmission, and everything else to make it work. And then the actual coroutine is the thing that does the work. So you have the engine, right? If you have a car, you can't run the car if you don't have an engine in it. But if you just have the engine, you also can't drive just an engine. You can't just sit on top of it and go. You need to put it inside of a car to actually make it work. So you need both of them to make everything work. And, you know, in order to do that, there's a concept of channels in a sense where when it comes to like sending data back and forth. So, let's say in a traditional world, what you'd normally do is if you have two threads, you would have what's called a thread local. And a thread local basically represents, all right, so I have this variable that is local to this thread only, and it's going to basically run. Oh shit! What? Sorry, my computer's like freaking out on the other screen. Basically, you'd have this variable that can only be accessible on that thread, and that basically prevents data races. And that's very nice, but if you want to share something between threads, in a traditional sense, you would have to use what's called a mutex. So if I do a search here for C++ mutex example, it's a very nasty way of doing it. So let me see if I can. All of these threads are calling the same function, and they're using a mutex to protect the read and write access of that actual function. So you basically lock that mutex, and then print out some data, and then unlock the mutex. And that's fine, right? But if, for instance, let's say, you want to pass or you want to send data from one thread to another, and maybe let's say you want to send data from one thread to maybe two threads. So now you have a more complicated problem in order to solve that. So channels are just a little bit easier because you can just basically say, I want to take this piece of data and send it off through the channel, and then whoever receives it will receive it and do whatever they need to do with it. So you can see here you have like a coroutine. You pass your data into that channel, and then the other side receives it. And all this stuff works in the same way. It does use mutexes to lock it, and we'll see that in a second. But this is just one of those things that you want to think about when it comes to actually building your system. So here's an example of how like coroutines work together. I like to think of this concept as called cooperative multitasking. Basically, cooperative multitasking states, at least in my programming language, basically you have something that you want to send to another thread through a channel. You acquire the mutex to the actual channel to send the data to it. Once you access that channel and access that mutex, you put the data on there, you release the mutex. Then let's say you have two threads that are trying to access, or two coroutines that are trying to access that channel. Well, let's say you have both coroutines running on the same thread. Well, what it's going to do is once data has been sent on this channel, and once a coroutine is ready to actually process that, it's going to be waiting and it's going to gain access to that mutex. Well, let's say it actually locked it and then unlocked it before it got a chance to actually receive anything. So if we have like this barista 1, it would lock it, it would wait for a few seconds and then unlock it and go to sleep. And then the other one would then get the opportunity to lock it and try to also inspect it as well. So they would basically both be fighting for the opportunity to be able to pull data off of that channel. And whoever gets to it first will get to it. So we'll see that in a second. But yeah, so that's kind of, and I know I'm probably doing a bad job at explaining this. There's various different types of channels. So I'm just gonna like go through the code to like explain a little bit better. Okay, so when it comes to building your coroutine system, the first thing you need to do is you need to build the API. So obviously we've talked about the task scheduling API before. I don't have to go over that again. I've already made a video on that. But there is some things different that I did do. So if I go to channel, this is the ability to allow us to send data between threads through this channel. So this is something that newer programming languages like the Go programming language, Kotlin also uses this concept as well. So you have what's called a receive channel and a send channel. And these are two interfaces that, let's see, so if I go to send channel, these are two interfaces that we use to do work on the actual channel, and you want to abstract away from the actual work or the actual source code that handles the actual implementation of what each of these functions do, because you just want to have the simpler version of it. So like, let's say you have a channel that you're using and you have multiple threads using it or multiple coroutines. The coroutines that are supposed to listen to that channel should only have access to that variable as if it is a read channel, or receive channel, not read channel. And then anything that wants to send it can either use the channel object directly, or it can cast that to a send channel. So for send channels, you can send data. You can send data on what's called a filter. You can close the channel and you can open the channel. So if I go to, where is it at? I keep getting lost here. It's kind of ridiculous. So if I go to receive channel has a little bit more functionality. So you can read data. You can read data on a filter. You can read the next set of items on a filter. So we have both of those. You could read a certain amount of items on a specific filter, or you could just read until the channel is closed. You also have read all, and then the next piece of data or the next sub channel that's open. And then we also have available data. So let's actually see how some of this works. So we have a couple variables here. So you want to create a list of filters. The way that I do this is basically the way it works is you have, what's called the master channel. So you have a channel and you can set the, the type of channel, the buffer type. So you have your master channel, and this master channel then has what's called sub channels. And these sub channels have their own filter address, or filter ID. You kind of think of it. I kind of think of them as sub channels with their own filter addresses. So we have sub channel 0, 1, and 2. And what this allows you to do is this allows you to have individual data sent to each of those types of channels. And if you have, let's say, 5 coroutines that are listening on a single channel, well, you could create 5 of these. So we could say 3 and then 4. Obviously it's 0 based, so 0 to 4 is a total of 5. So you can create a total of 5 subchannels, which will allow you to basically send information to each of these subchannels independently, and you don't have any what's called blocking with the channel. So if I go down here, so you can basically construct it multiple different ways. You can pass it the capacity, which is the amount of subchannels you want. You can also pass the capacity and then the amount of filters. You can also do some other stuff as well, like the buffer type, amount of filters. And then you can get the capacity of the actual subchannels. You can get the buffer type. You can also check to see if it's closed, send channel, send data through it. And the whole purpose of this, I don't want to go through all the code because this video, I mean, even though it is live stream, it's gonna be a little too boring. I don't want it to be too long. So when it comes to actually sending data, you can potentially have what's called a blocking situation. So each subchannel has what's called a buffer, right? And I have various different types of buffers. So I have what's called an exclusive buffer, single buffer, unlimited, and buffered buffer. And you want to, whenever you create your channel system, you want to make sure that you have this because then, you can basically uh, have control over how your data is processed. So if we look at the first one, exclusive buffer, an exclusive buffer states that you can only have one item in that buffer at a time. So it's a list with only a single item on a subchannel. And once an item has been placed on this buffer, the thread that's actually listening for this item has to accept the item immediately and take it off the buffer in order for the thread that's sending the data to not be blocking. So what this is called a blocking call. So I'm going to put a star here. So I'm going to put a index so we could like say the star is equal to blocking. So if I have a star here, that means this is a blocking buffer. So if the buffer is full, aka since it's only a single buffer, once you put data on it, the buffer is full, the thread needs to accept it, that's listening to it in order for this to be sent successfully. We also have single buffers, which this one, so if you have a single buffer, this one is a set it and forget it. So if we have, let's say we send 1 through this buffer, and then let's say we send 2. Well, if the thread didn't read the first item, then it's going to read 2 instead of 1 because it just lost that data, because we're just like blasting it with data and not really caring, whether or not the thread that's listening for it is actually listening for all of the data. So this one just kind of overrides the previous amount. By the way, Kotlin does all this stuff as well, so I'm just basing it off of that language. We also have unlimited buffers. Unlimited buffers are as they are, or are as they sound. So you can have item, and you can just basically have an unlimited amount. Now, it's actually not unlimited because obviously memory is not unlimited. So what's actually going to happen is, as you know, your programming language is going to have a memory limit. Once that memory limit has been hit, you get an out of memory exception, which basically that's the end of it. So if you slap 100 million items in this list and you run out of memory, then you'll get an out of memory exception. So that's how that works. And then finally we have buffered. Now buffered is as it sounds. So we can have, let's say, a buffer of 3 items. Basically what's going to happen is this is also considered a blocking type of channel. So if the thread that's sending it sends 1 as the first item, and then 2 as the second item, it's totally fine. But once it sends 3 as the third item, and then let's say it tries to send 4, right? So let's say it tries to send 4 as like the next item. It's not going to be able to do that because there's no space. So what's going to happen is the thread that's trying to send the data is going to block because there's no more size in the buffer. So once the thread accepts it, then it can put 4 on the list, and then the thread can consume all these pieces of data. So again, just something you want to think about when it comes to actually building this. So definitely do that. Once you have this channel system completed, though, the next thing you'll want to do is you also want to create a coroutines system. Now, like I said, I've already gone over this, but I will go over the fiber system. So basically what this does is you want to create a concept of, the actual high-level version of a coroutine in the programming language. So the technical term for my stuff is called fibers. And I've already explained, why that is. Basically, a fiber, you can think of it like you have a thread or you have like a rope that represents the actual thread or the actual, yeah. So you have like a rope that, and then you have a bunch of fibers that, go around the actual rope to make the rope itself. And the fibers are what actually makes up the rope in the same sense that, you know, if you have a thread by itself can't do anything, right? It's not really doing any work. But if you have a bunch of fibers running on that thread, now you have work being done on it, aka, you know, that's why it's named that. So you want to have for fibers the name, the ID, the main function, the exit value, and the thread that it's bound to. Now, I've mentioned before, threads or fibers specifically can be bounded or unbounded. Basically, what this means is, and other languages have this concept as well. I think Kotlin does, but I've never seen something like that in Go before, so I'm not sure about that. But basically, if you have a thread that you want to attach this fiber to, and you only want to run this coroutine on that thread, then you can bind it to that thread. Otherwise, it's just going to bounce around forever, and it's going to run on any thread that's available. And you want to, you know, have the ability to do all the same things on a coroutine as you can on your threading system. So one recommendation that I would make is, first, obviously, you need to build your threading system first. And I've already gone over countless videos of how my threading system works in this low level, in the actual virtual machine itself. But once you kind of have that and you have your high level API for doing stuff with threads, you literally just copy and paste the same crap. The only difference is that you're going to have a few different types of functions. Like we have bind here. And my process for creating all this is very simple. I literally just took the thread.sharp file, copied it, pasted it into here, and then removed the crap that I didn't need. I don't need as many fields as threads. So like threads are really complicated and they're very expensive. So as you can see, the overhead for threads is a lot larger. And that's another thing you want to think about too. So when it comes to thinking about overhead, you're going to run into this issue very quickly if you try to scale this. What the Go programming language does is Go, I think, has a 4 kilobyte size for all of their coroutines. And this is fine, right? So to contrast this with threads, in my current programming language, a thread takes up a total of 1 megabyte of memory. So if we have a thread that takes up 1 megabyte, then if we have a coroutine or a fiber, which is the technical term for it, that's going to take up a total of 6 kilobytes. So I tried to get my system as close to Go as possible because, you know, Go is like one of the leading programming languages in concurrency right now. So Go has, like I said, 4 kilobytes, mine is 6 kilobytes. So this is the total amount of size that each coroutine is going to take up per coroutine. And this is very important because, again, as you scale up, this means that for every 10,000 of these, what is that, like 6 megs or 60 megs, it's going to scale up in direct proportion to this. Now, what this is known as what's called the starting size. So if I say starting size, this is known as the starting size of each coroutine. So as you basically call more functions, you will have a much bigger coroutine. But what you want to do is, when you build this system, you want to build it in a sense where all of the overhead, all these functions that you create for it, you want to do it in a sense where you can have enough information about the coroutine itself and the most barest amount of information that you need to make it function, but you don't want to give excess amount of information, because what else do you need to run a coroutine? You need a stack to run it, right? You need a call stack and a actual like memory stack. That's how my programming language works, just to make it a little easier. You also need a bunch of other things as well. So if I go to the runtime, then fiber.h, as you can see here, it's quite a bit of overhead. So all of this stuff, once you build your threading system, again, copy and paste the code. When I build all of my systems in my programming language, I do not try and reinvent the wheel. I don't try to be smart about it. I literally just took all of the fields that were inside of this threading object and pasted all this crap into here. So I copied the exact same data structure and just pasted in the stuff in here in C++, and then removed what I didn't want or didn't need. So you want to contrast this with the high-level version of your actual coroutine. And you don't need nowhere near as much information at the high level as you do at the low level, because you need stuff like the state of the fiber, the program counter that we're executing, the stack pointer, the frame pointer. You don't need all that stuff at the high level. All you need is what's the name of the coroutine, what's the native handle to the coroutine at the low level, what's the main function, and this other stuff. So keep that in mind when it comes to building it, because not only are you going to have low level overhead where every time we create a coroutine, we need to create this class, we're also going to have high level overhead as well. So, obviously this object takes up physical memory in the programming language, and you have to take that into account as well. So do not bloat your stuff with a bunch of garbage. I mean, obviously when you first start it, you want to, be able to see what's going on. But once you kind of get it working, then optimize it and remove all, like basically trim the fat. Um, so another concept that you're going to want to do is you're going to want to add the concept of delay. So, I have all this stuff. I mean, we've already gone over the threading system. I'm pretty sure some of you guys have already seen some of these functions. You can suspend them. You can unsuspend them just like threads. You can kill them just like threads. You can join them just like threads. They're exactly the same thing. The only new stuff is bind, unbind, which is the reverse of binding it to a thread. We also have the ability to get the state. Well, thread has that as well. You can get the state of the thread. We also have the current, so you can get the current coroutine that we're executing in real time. You can also poll. This is also something new. So when it comes to coroutines, you want to be able to see how many coroutines are what's called bounded to a specific thread. And what that allows you to do is that allows you to assess the load on that thread. The more coroutines that are binded to a specific thread, the higher the load is on that thread, meaning that the harder the thread is going to have to work to actually execute all of those coroutines. If you have a lot less binded threads, like let's say you have like 10 binded threads or binded coroutines to a thread, it's going to be a lot easier than if you have like 20,000 binded to a single thread, because then it really has to work hard at making sure everything gets executed. And then finally, you're going to want to have a concept of delay. So delay is a little bit different, and this is literally the last thing that I'm going to show you before we like jump to the low level. It's really simple, guys. It's not that complicated. So where's that? Actually, I'll just explain it. I'm not going to like hunt down the actual function. Basically, what delay does is, in a traditional sense, what you do is you'd say thread dot sleep, right? You can sleep for 1,000 milliseconds. I'm pretty sure you guys have seen that before. What this does is this is a blocking call, and it basically just stops execution on that thread, right? So this thread at the low level sleeps. So basically you're providing time slices to every other thread. So if you have 4 threads running, you sleep for 1,000 milliseconds. Well, you're going to have basically 3 threads running on that processor for those 1,000 milliseconds. And then eventually, once that time is up, the scheduling system will schedule this thread to be executed again. But unlike that, so if I actually keep that, what delay does is, let's say we have a thread. Let's call this thread, I don't know, foo, because I'm bad at names. Let's say this thread has coroutine 1, coroutine number 1, and then let's say, we have 2 coroutines running on here. Let's say coroutine 1 calls the delay for 1,000 milliseconds. Right? So this coroutine calls delay. What's going to happen is the thread is executing coroutine 1. It's basically just going to swap to executing this coroutine, and it's going to perform what's called a context switch. And a context switch is basically a swap from one coroutine to another. And this allows you to basically run this one, and then let's say this one then calls delay as well. So if this one calls delay of 1,000 milliseconds, now what's going to happen is they're both going to be asleep, and basically this thread is not going to have anything to run until both of these finish delaying. So if we call this, it delays, and then we call this and it delays immediately, the thread's just going to be doing nothing. So it's going to be running at 0% CPU utilization. And obviously, there's a little bit of time. So like basically, this one's going to delay first, and then this one is going to run because it's going to take some time to context switch to that one. So it'll just basically continuously swap between the two indefinitely. So, that's something else you want to integrate. So let's actually go into the source code. So what you want to do is you want to create a scheduler. Now, this is how the entire system is going to work. So I've been able to increase the limit. So I know I kind of mentioned before, we could execute up to 20 coroutines per second. Now I'm going to explain how I was able to actually increase the limit. The way that I was able to do it is basically before I had these three defined statements here. Low priority time slice interval. This is a acronym for that. That's what LPSTI. Normal priority time slice interval. Here's the actual name right here. And high priority time slice interval. What these were denominated in originally, these were denominated in milliseconds. And originally, I do not remember what the, and I don't want to go searching for it because I've probably committed at least 100 times, so I wouldn't be able to find it. But originally, low priority had a, I think it was a 25 millisecond time slice. Normal priority had a, maybe like 50 millisecond. No, it was 70. I remember now. So I had a 70 millisecond time slice. And then for high priority, I had like a 110 millisecond time slice. Well, that's been scrapped. Now what I do is I operate in what's called microseconds, which is, US. That's the actual acronym. So you got, milliseconds, you got seconds, and then you have microseconds. Below microseconds, you have nanoseconds, but the programming language is not that fast. I can't go that low. And this basically allows me to execute, for low priority threads up to a maximum of 2,000 fibers per second. For normal priority, this allows up to 1,000 fibers per second. And then for high priority, up to 666 fibers per second, because this is 1.5 milliseconds, 1 millisecond, and then half a millisecond. Now, I know what you're probably thinking, well, okay, then if that's the case, how am I able to execute, 100,000 basically coroutines per second? Well, that uses the concept of what I call cooperative multitasking. And I'll get into that in a second, but basically you have all these, and then I have the clock cycle, and this is a high resolution clock cycle that basically sleeps the scheduler every 50 microseconds. So it's very accurate when it comes to actually scheduling the context switches. So before we get into the really complicated stuff, I have a cross-platform micro sleep function. I highly recommend you checking it out. I don't need that anymore. Highly recommend you checking it out. Basically, what it does is on Windows, you can't sleep for microseconds. Like, it's impossible. If you, well, it's not impossible, but there's no standardized way to actually do it. So if you say sleep on Windows, this is the Windows function, you pass in milliseconds, right? But I needed to be able to sleep for microseconds. So the way that I do it is I yield first, because this function does get called a lot. I create a handle of a timer, large integer. I do some stuff. To be honest, I found this online. I have no idea like what any of this stuff does. It, I guess, creates some data structure. You pass it what microseconds you want to execute it, and then you set a wait timer, I guess, and then you just wait for that object for X amount of time. And because it's because no object is going to because no other thread is going to release the lock to this, you're basically just waiting for no reason because it's not a shared object. So there's not going to be like a release on the actual object. So we just wait for that amount of time, then we close the handle. And it's very accurate, so I've been able to integrate all this stuff. For Linux, I just call yield and then usleep, and that's it. Now, and this is going to be in the scheduler.cpp, by the way, in the actual programming language. You can head over to the concurrency branch. I've been working out of the concurrency branch for months, at least the past like month and a half, 2 months. I don't really work in the remastered branch for now because I'm trying to get this concurrency stuff working before I merge it into that branch. And I'm also doing concurrency JIT. This is with the JIT code. I'm going to merge this JIT stuff into the concurrency branch, and then merge the concurrency branch crap into the remastered branch, and then delete all those concurrency branches. So that's my plan to do that for anybody who is looking to look at the code. But here's how the scheduler works. It's very simple. We have what's called a thread release block. And what this does is basically we have one single source of truth when it comes to managing all the threads. Previously, before, threads could manage themselves, and they still kind of do. But when it comes to releasing those threads, like when it actually comes to accessing the list and removing those values, I only have one thread to do that. Previously, before, a thread could like access the list and remove the value, but that doesn't work anymore because if a thread tries to, let's say a thread was running and then it ended execution in the middle of the program executing, the scheduler is actually running and accessing all of these threads, and it's trying to force those threads to context switch. And that's not going to work if I have threads like freeing themselves, because then I'm going to be accessing freed memory, and that's not going to work. So basically, a thread can add themselves to the list, but in order for a thread to be removed from the list, the main thread that's running the scheduler has to handle that. So I just want to mention that because that is a huge bug that I had to deal with. So basically what I do is I increase the clock. So every roughly, so I do clocks percent 1,000 is equal to 0. So if we say 1,000 times 50, that is every 50 milliseconds roughly, I try to dispose the fibers. Now, I guess first I'd probably have to talk about like how we actually create the fibers. Okay, so before we get into that, so create the scheduler source code, like just the function, and then before you do that, you have to create the fiber system because otherwise this isn't going to make sense. So let's start at the very first point. So what you want to do is you want to be able to build a fiber or a coroutine. So in order to do that, you need to pass it the name and the main method that we're going to execute. Now, how do I connect this to the programming language? You guys know, I'm pretty sure you know how I'm going to do it. I go to the virtual machine, I go to system interrupt, and I literally just add another case statement here called, I don't know what it's called, fiber start. And I also have the delay function as well. Fiber start, and I basically just pass it all the crap that I need from the stack. So depending on how you guys stack works, you want to be able to pull those objects directly off, such as the name, the main function, the thread that you want to bind it to, and any other information that you want to pass to your coroutine. And I have a way to actually pull that data off of the actual objects themselves. And then I access the thread, and then I basically just try to, after I create it, I basically set the fiber object, and I also set, what is this, the args to that fiber as well. So if you guys remember, whenever we created a thread, we had to set the thread object, and then we also had to set the arguments to that thread, so that way whenever we access the thread arguments, we could do that. Well, this is the exact same way. So if I have thread start, you can see here the current thread and the args. It's literally the same crap. All this stuff that I'm doing, I just copied and pasted the way that the threading system works. It's just slightly tweaked. We'll start to see how they diverge in a second though. But yeah, so once you do that, then we basically bind it if there's a thread. So we say bind, we pass the thread. If the thread is not equal to null, then we basically we gain access to the thread's mutex. We make sure the thread is not dead, and then we say unbounded fibers minus minus. So we have this boolean here. We basically want to keep track of how many unbound fibers that we have in our system. Fibers that are just running around stealing all of the execution of everything of each thread, because unbounded fibers don't have any rules as to what thread it can run on. So we want to keep track of that. and then we just set the bound thread, and then we increase the bound fibers on the actual thread itself. So we also want to keep track of how many bound fibers are in a thread, so that way if we poll a thread to see what's the load that's being applied to that thread, we can do that. And we also want to check to see if so if the thread is equal to null, we want to check to see if we are already previously bound to a thread. This is how you can quote unquote unbind a coroutine to a thread. You access the thread's mutex, you increase the amount of unbounded fibers because now we have a fiber that's not bound to anything, and then we basically subtract the bound fibers from that thread, and that's it. And then we set our bound thread to null and we return. So that's how we basically bind threads in the programming language. But now let's go back to how we actually create fibers. So I malloc a single fiber. I probably should check to see if that's null. Yeah, I'm gonna put to do here. That's like one of the most basic things you need to do in C++. Check to see if fib is null first. As you can see, you don't have to be super smart to like do all this stuff. Like, I just try something and throw a bunch of spaghetti at the wall and see what sticks. Hopefully I'm explaining this good. If you guys have any questions, like I said, you can just put it in the comment section below. Most likely, most of you will watch this after the stream has ended. But you want to set up all your stuff. So I'm not going to go through all these variables, but you can see I'm just setting them to the default values. For fibers, I will go through the highlights because most of these variables, I literally just copied them and took them out of the threading object. So the way that it works is if we have a thread, now instead of the threads actually executing stuff, once you create a single thread, the thread will then immediately create a fiber to run that thread. So in order to run a thread at all, you need at least one fiber to run on that thread, and that represents the connection for that thread to actually execute. And once that thread has no more fibers that are bound to that thread, then you basically just that thread dies basically because the assumption is that there's nothing to run the data. Despite even if there were unbounded threads, the unbounded threads will just steal data from or time slices from other threads. So the things that are different with coroutines that we did not have with threads are: one, delay time. If you delay a thread or a coroutine, you need to specify how long you want that coroutine to be asleep for. We have Wakeable. So this is a concept where basically if you suspend a thread, you don't want that thread to then run again, because threads can, or I keep saying threads, coroutines can be suspended at any point during execution because their time slices up, right? Like if a coroutine's running for 5 milliseconds, that's way above the time slice, and that's entirely possible. We might be doing something, writing to a file, and it just took a while, whatever. Once a coroutine runs past its time slice, it needs to context switch, and in order to context switch, we have to suspend the coroutine. So if we set wakeable to false, that means we can't wake it up out of suspension once it's been suspended. So that's what that is. We also have finished, whether or not the coroutine is finished execution, very obvious. Locking, this is the magic behind how everything works. So previously, I mentioned, again, for a high priority thread, you can only execute up to 600 coroutines per thread. Well, how is it possible then on a high priority thread that I can execute, 100,000 coroutines per thread? Well, the way that it works is it uses cooperative multitasking. And basically what that means is if we have a coroutine, and you guys please implement this in your system as well, because it's going to speed it up a lot and allow you to scale to a lot more amount of coroutines per second that your system can handle. When a coroutine tries to acquire a mutex to an object, if I am on thread A, right, and I have two coroutines running on that thread, thread, the first coroutine tries to access a mutex lock. It locks the mutex, totally fine, right? It does some work and it's doing work for a really long time, and then let's say it gets put to sleep because it ran past its time slice. Now coroutine 2 must be swapped out for coroutine 1. Let's say coroutine 2 then also tries to lock the mutex that coroutine 1 has access to on that thread. Well, that's not going to work because the coroutine 1 has just been suspended. And it wouldn't make sense for us to just keep spinning forever if we literally know that if we just swap back to the coroutine 1, we can run that a little bit more. Ideally, the mutex will be released, and then when we swap to coroutine 2, we can gain access to that mutex. So what this means is if there is a thread or a coroutine that's locking, there's a high chance that that coroutine is should not be ran. So what's going to happen is we're going to take coroutine 2, try to gain access to the mutex. It's going to see that coroutine 1 owns that mutex. It's going to suspend itself voluntarily and try to attempt to switch to the first coroutine. Once it does that, then it basically is going to, the system is going to for loop through the entire list of coroutines. Let's say it starts at the coroutine 2. It's going to see that coroutine 2 is locking. It's going to skip that, jump to the first one, and then run the first one. The first one then, like I said, releases the mutex, and then the second one runs, and that's how the process works. So the system tries to cooperate with the high level to make sure that all this stuff works. We also have marked, by the way, the Go programming language does this as well. It has its own concept of like cooperative multitasking. So I pulled that concept from the Go programming language, if any of you are wondering. Finally, we have marked. Marked is a way I do a mark and sweep for coroutines because you don't want to destroy a coroutine instantly, immediately. You want to kind of wait to destroy it because there's a certain amount of time that it's going to take to actually destroy that coroutine because maybe it's doing some cleanup or something as it's finishing execution. So that's how I do that, and then all this other crap is the same. We got the call stack, the registers, the data stack, the fiber object, exception object, bound thread is new, so that's something different. All this other crap is the same. Now, how do I manage the stack? Here's another thing that you want to do when it comes to creating the stack. So I have what's called a dynamic stack allocation system. Basically, the way that this works is you have, your initial frame size, which allows for the size of each coroutine to be a total of 6 kilobytes, right? That's the initial size. And the way that I figured out that number is we basically have an initial frame size and an initial stack size. So the initial stack size is roughly 4 kilobytes. The initial frame size is roughly 2 kilobytes. 4 plus 2 is 6, 6 kilobytes. That's the default size of every coroutine. And this basically allows us to have the minimal amount of memory that we need for our coroutine to function. Because if you really think about it, right, what this is telling us is telling us right here that we can execute up to basically 50 functions nested deep. Now, under normal circumstances, you're not going to run source code that recursively, right? So if you know that your programming language isn't going to be built for recursive execution, well, I mean, every programming language is that, but like more specifically, if you know that your coroutine is not going to be doing anything recursive, it's okay to set the initial frame size to 50 functions nested deep because that's going to handle like probably 70 to 80% of cases where you're never going to go further than that. So, it's just a very nice hack to allow that. And what we do is basically once we hit the limit of 50, so let's say we've called 50 functions nested deep, we need to now allocate more stack space so that way we can continue working on the coroutine. So we have what's called a frame grow size and a stack grow size. So we have the initial stack size, and then we have the grow size of each one. So I grow the frame by roughly 6 kilobytes or 150 functions nested deep. So if you execute 50 functions nested deep and you need to execute for whatever reason 51 functions, we're going to allocate 150 extra functions that you can call nested. Now, it's very unlikely that the user is going to execute 250 functions nested deep unless they're probably getting like a Stack Overflow exception or something. I don't know. That's entirely possible. But yeah, so that's what I do. And that's about 6 kilobytes. And the frame size is very expensive to allocate because it's a lot of memory. So I try to keep it very low and reasonable. Same thing for the stack. So I do 512, which basically is 512 slots of data for the stack. And yeah, so that's about 8 kilobytes. So in total, theoretically, if you call 50 functions nested deep and you keep doing that, you're going to allocate roughly 8 plus 16, which, yeah, I'm bad at math. What is that? 8 plus 16, or, oh, that's 8 plus 6. Okay, so I'm blind as well. That's 14. So you're going to basically allocate every time 14 kilobytes of memory to expand the stack. So that's also something you want to keep in mind when it comes to actually building a system. So what you want to do is you basically have this here. You want to make sure that you want to basically just allocate the default stack size. So you want to check to see if the amount of thread locals that you have is less than the stack size, the initial stack size. And this is going to basically, if you guys remember, thread locals take up stack space every time when you create one, because that it's like you have the so you have the stack, which has slots here, and these represent the thread local space, local space. And then we also have the user space, which now represents all the stack slots for any functions that the user calls. So we have the thread local space as the first 3. So if you have 3 thread locals total, you're going to take up 3 slots by default in the actual system. Then any functions that you call after that, you're going to take up additional. So you want to make sure that you at least have enough slots to fit the thread locals. And what I do is I do plus 50. Let me go back here. So I do plus 50, which, the initial stack size is about 250, but I do an additional 50 just to make sure that there's a little bit of buffer, so that way the system has time to allocate more memory. And based off of that, based off of those checks, if we're less than with the thread locals included, then we set our stack size here. Otherwise, I also check the internal stack size as well. This is basically just the total default stack size of the system. If the total default stack size of the system is less than the initial stack size, we could also do that as well. So what you could do is you could say dash I stack 2 kilobytes, right? Which would basically allocate 2 kilobytes, and that's less than the total initial stack size, which is a total of 4 kilobytes. So I also check that as well. Once you do all that, then you want to allocate the stack, and then you want to initialize the values this way. Now I could have just did calloc, to be honest, but yeah, you just want to make sure you initialize all the values here. And then once you do that, you want to do the same thing for the call stack. So do the same checks to make sure that you have space for everything. And then you allocate the call stack based off of whatever criteria you want. And then you want to make sure you add this memory. So every time we create a new coroutine, we add the initial memory to the system, to the garbage collection system. So, this is another thing that it's really tough to balance. You want to balance performance and the ability to be able to create a bunch of these without causing a ton of garbage collections. Now, I've recently raised the limit to my garbage collection system to basically, I think, 250 kilobytes, or 250 megs actually, as its default value. Previously, before, I think it was like 64 megs. So I've increased it so that way you can create a decent amount of these without ever having any issues. But just know that eventually you will run out of memory if you continuously create these coroutines. Then finally you want to add the fiber. Once you do that, the way that I do is I have a list of coroutines. I get the data size up here. So you want to create a bunch of variables. You want to create the fiber ID, which is going to be a unique ID for each coroutine. How many coroutines we have active, what's the total capacity of the list size. Max passes is a variable that checks, so basically whenever you have a locked coroutine, you basically skip it once and you execute it the next time after that. We also have resize min, resize max. So when it comes to actually resizing a coroutine list, I have a resize min of 2500. So basically, I have a list of fibers, which is an atomic pointer to a list of fibers, which represents the actual fibers list. And it's just that pointer, so you can just access it as an array. And I use an atomic to make sure that reads and writes aren't screwed up because we have tons of threads accessing this variable. We also have a fiber mutex as well, and then a couple other variables for keeping track of the state of things. How many spots we have open, how many fibers that we have stale, which needs to be freed up, and how many unbound fibers that we have. The stale fibers is used by the scheduling system, and yeah. So when it comes to adding a fiber, we go through the list and we check to see if a slot is equal to null. This will be possible if we freed up a fiber. We'll see that in a second. We lock the mutex, and then we decrease the open spots, and then I check here if open spots is greater than 0, just to make sure I read on this atomic integer, just to make sure that we have any open spots available. If so, then we do whatever we need to do. We just add it there. Otherwise, I check to see if we have capacity, so I increase the capacity of it. So the way that I do that is when I increase the fibers, this is as we're scaling up, I basically try to scale as fast as possible to support creating hundreds of thousands of these coroutines. Basically what you want to do is you want to get the resize amount. You want to set it to, if the capacity is equal to 0, you set it to the resize max. So basically what that does is right off the bat, I create 25,000 slots. Oh, that's kind of stupid. That's supposed to be resize min. Whoops. Well, basically, I set it to the resize min, which is 2,500 slots. And then after that, if capacity is not 0, then I say capacity is equal to capacity plus resize min. And I keep doing that up till the resize max, which is 25,000. So I keep growing it, and eventually you'll just allocate 25,000 slots for coroutines every time. Now, this is allocating space for pointers. This is not actually allocating 25,000 coroutines. This is allocating spots for the pointer of each coroutine that we create to be there. And I allocate the data. I get the old amount of fibers. I store the temp fibers, so I reset the value. And then I update temp fibers with the old data. And then that's pretty much it. And then I set the capacity or I increase it to the resize amount. And then I free up the old pointer, and then I add the memory. So I add it to the resize amount because that's the memory that we've added. And then when it comes to decreasing the fibers, basically what I do is I set the resize amount equal to the data size of how many coroutines we have currently. And then I add that plus 25% of the capacity. So, if we have 500 coroutines and a capacity of 2,500, I say 500 plus whatever 25% of the capacity is. So at a minimum, we will always keep 25% of the capacity. That way we're not constantly allocating and deallocating all the time. Yeah, and same thing here. I literally just call alloc, which is less than the amount of what we had before, and then I just allocate that, store the values, update it, and then free the memory on the garbage collection that we passed in here. So that's the basic premise of how that works. Now let's go back to the scheduler. So when it comes to the scheduler, we call dispose fibers every 50 milliseconds. We check to see if we have any stale fibers, meaning that we have fibers that need to be freed up. If so, then we for loop, because it doesn't make sense for us to like waste processing power. Like what if you have a million of these, right? And none of them have finished executing? It does not make sense to for loop through a list of a million coroutines every 50 milliseconds if there's nothing to free up. Um, so, we have the data size, and then we for loop through that, and then we check to see if the fiber at a specific index, or we get the fiber at a specific index. We want to make sure that the system is not down. And here's the criteria that I figure out whether or not we need to free the actual coroutine. If the coroutine is finished, its state is killed, and it's not attached to a specific thread, then we can free it. Now I have a concept of binding and attachment. Binding to a thread means that you will only execute on that thread. Attaching to a thread is whatever thread we're currently on. So that's how it works, right? So if you're bounded to a thread, that's basically the only thread you can run on. But if you're attached to a thread, you can be attached to any specific thread at any time during execution. So it's just whatever current thread is running this coroutine. So yeah, and then to free it, we just set the item to null. That's where we get the null from. We guard the mutex, and then we update stale fibers in open spots, and we free up the coroutine and free it. Now this free function literally was just copy and pasted it from the terminate function from thread. So I have this terminate function here. It's a lot smaller. I just rip the code from there and just paste it in here. It's the same crap. So nothing has changed here. Everything's the same. And now when it comes to this, I mark it first. So if I see if the fiber is marked, I free it. Otherwise, I mark the fiber just to make sure that no thread is running this coroutine, because if I free a coroutine while the thread is executing it, that's catastrophic. So you don't want to do that. Then finally, I decrease the fibers. We already went over that function, so that's how that works. Now here's how the system works. First, what I do is I get the size of the total amount of threads that we have. And I basically get the logged time. The logged time is basically the current time in microseconds that we're running all this code. And the scheduler runs in microseconds, so it's very accurate when it comes to scheduling all these things. So what I do is I check to see if the current thread is equal to the garbage collector or the just-in-time compiler thread. I just bounce over it because it doesn't make sense to try to interact with that thread because it's going to ignore it. Now, the way that this system works is it works on a consensual basis. The scheduler can try to tell the thread, I need you to switch to a different coroutine. It's time, your time slice has been passed. But if the thread basically tells the scheduler to screw off, then nothing happens. So the scheduler does not have any power in terms of actually making the threads context switch. So, and we'll see that in a second. But basically, we want to make sure the system isn't down. And the criteria for, before we get to that, if the system is not down and the thread is killed, then here's where we actually kill it. We check to see if the thread release block is set to true. Now, where this value is accessed and set is when the garbage collector calls suspend all threads. So if you remember, when the garbage collector is about to collect, it needs to shut down the system temporarily. So it suspends everything, and what that does is it calls a thread release block and it sets that value to true. Now, the reason why I'm not just guarding the mutex here is because it's going to slow the whole system down, right? Like because multiple things are using this threadless mutex. It's not just, the scheduler and the garbage collector. It's also threads. Like, what if I'm creating a bunch of threads, like physical operating system threads? It's going to slow the whole system down. So I use this atomic integer, set it to true if I'm collecting, set it to false once I'm done collecting. And that's basically how it works. So if that is set to false, then I access the mutex, kill any bound fibers and then destroy the actual thread. So what this does is basically just for loops do, and it kills each coroutine that is running on that thread. So yeah, and in order to actually check that, I make sure that the fibers bound thread is equal to the current thread. So I for loop through the entire coroutine list, and if the coroutine is bound to the current thread that we passed in here, and the state is not killed, and the fiber is not equal to the current fiber that we're executing, I have a concept of this fiber, we'll get into it in a second, then I kill that fiber. I pass the ID, it gets that fiber, which is kind of stupid, but yeah, so I kill that fiber. The way I kill fibers is I basically just set the state. So it's basically a software-based, like it doesn't actually, that was kind of a silly term, but it doesn't actually do anything. It just changes the state of the fiber. And the only way you can kill a fiber is it has to be suspended or running. So if it's suspended, then we set the state to killed, and that's it. If a fiber is suspended, that means it's not running on any one single thread, and it's just safe to just change the state. And when threads try to execute this coroutine, they're not going to do it because it's a killed coroutine, and there's no point in running it. Now, if it's running, what we do is we try to force a context switch. So what we do is we set if the attached thread is true, I set the state of the fiber to killed, and then I basically enable a context switch. Now I do need to do some updates on this code, because theoretically you could kill a fiber and the thread can tell the system to screw off. So I am going to fix that, but basically what it does to enable a context switch is it sends a signal of tsig context switch to whatever you pass in here, and that's it. Just like when we send a signal to kill a thread, we just send the signal of tsig thread kill. It's the same stuff. I just added a new item to the signal enum, and that's pretty much it. So we try to context switch the thread, and if it's not attached to a thread, then we return 2, because that doesn't make any sense. You can't be running and not attached to a thread. That's impossible. So this should never happen, but it's just there as a precaution. Otherwise, if it's not suspended or running, we just set the state to killed, because I guess the only other state for fibers is created. So if it's running or suspended, then we do whatever we need to do. If it's created, we just kill it. If it's killed, it just gets killed again, I guess. So there's that. So that's how we kill a fiber, and that's how we kill all the bound fibers to a specific thread. So that's how we shut down a thread, and then we just call thread destroy. We've already gone over this function. It basically just pops the thread off the list, calls terminate, which terminates any variables that are inside the threading object. We've already gone over that code, so I don't think I need to go over that again. If you guys are curious, I've done tons of videos on my multi-threading platform, and none of that code has changed. I'm only going over stuff that's like new that I haven't done before. And then we just call continue, because obviously, we need to skip this thread. But after that, then we, if the state of the thread is not running, so if the thread is suspended, it doesn't make sense to try to context switch the thread. Now, here's the criteria that I come up with when it comes to telling the thread to context switch. If what is this? Unbound fibers. Where's this being used? Oh, okay. Okay, this is used here. Okay, so we have this unbound fibers in the actual, where's the fiber source code? I scroll up to the top. So I have this unbound fibers here that I created, which is an atomic int. That is used by the scheduler. So if the unbounded fibers is greater than 1, remember, unbounded fibers aren't constrained to a specific thread. It can run on any thread that's available. So if that's greater than 1, or the thread has more than one bound fiber to it, or the thread is waiting. Now, waiting is a Boolean, we'll see in a second, that shows whether or not the thread is context switching. And So if one of those are true, then the thread also has to be ready to context switch. You can't just, context switch it. So the criteria that I pick for whether or not a thread is ready to context switch is if the thread state is not equal to running, or it's killed, or it's suspended, I return false. Otherwise, based on the priority, I check to see if the current time minus the last ran microseconds, which is the microseconds since January 1st, 1970. Um, so this is going to give me the time difference since the last time that the thread ran and the current time, which is the logged time that I logged up here when I started this. And this runs in a loop, by the way. It's just a for loop, infinite for loop. And based on that, if that's greater than the time slice that's afforded to each priority, then that says, all right, now it's time to context switch. And literally all we do is we just call enable context switch and we set that to true. And that's it. So, and then after that, obviously I check to see again if the system is shut down. I wait if the system is shutting down, and then I wait until it's terminated, and I just sleep forever, and then I just return. And then after that, I just sleep. So I sleep for the clock cycle, which is 50 microseconds. I need some water. So I sleep for 50 microseconds, then I do it again. I'm going to stop really quick and get some water. Sorry, it's like super noisy. I'm like in my kitchen while I'm like doing the stream. Oh, that's much better. Okay, so since I know I'm sleeping for 50 microseconds, this guarantees that I run this scheduler every 50 microseconds. So once we do all that, now we're ready to actually implement the system. So this is the foundation, right? We have the fiber system, we've created the object, we've transferred all of the fields literally from thread to the fiber object here, all the fields that the thread used, such as the current method, the current stack pointer, frame limit, stack size, frame size, registers. Once we've transferred all those fields and did that, now we have these simple functions. So we have the ability to get a fiber, which locates a fiber based on an ID. We get the size of how many fibers are available. We for loop through it, we check the ID, and we return that fiber. Otherwise, we say null. After that, then we have a concept of, or before we get to that, because that's pretty complicated. So when it comes to suspending fibers, it's kind of similar to killing them. Literally what we do is we just guard the mutex. We check to see if the state is suspended. We set it to wakeable. So if we try to suspend a thread, we want to set it to not be wakeable because in order for a thread to be suspended, it has to be, we're basically saying we want to stop that from executing until we resume the actual fiber or the actual coroutine. So we just set wakeable to false. Now, if it's running and we're trying to suspend it, what happens is we set wakeable to false, we change the state to suspended, and then we enable context switch on that thread that's executing. And yeah, so that's how we do that. Otherwise, if it's any other state than suspended or running, we just complain about it because that doesn't make any sense. Obviously, we can't suspend a thread that's been killed. Now, in order to unsuspend it, it's very simple. If the state is suspended, great, we just set wakeable to true. Otherwise, we return 1 because we can only unsuspend something that's been suspended already. So there's that. And then, let's see, so we've gone over those functions. Let's look at growing the stack. So what I do is every time when I call a function, I check to see if, because as you know, right, like every time we create a function, let's say we have foo, right? And then let's say this takes a var, then another var, and then let's say a string, string. What this is going to do is this is going to take up a stack space of 3 elements. So what happens is when we call the function, it's not just enough to, as we're pushing data on this function, first we have to push 5, then we have to push, 10, then we have to push hello. It's not just enough to be able to check to see if we've blown over the limit of the current size of the stack as we're pushing data. We also have to check to see if we have enough space for any local variables in here. So let's say in here I had, 5 local variables. If that's the case, then not only is it going to take 3 items to push the local arguments on here, we also need 5 slots for any local variables. So we need to check to see if we have, whatever the current stack pointer is plus 5, and if that is less than the limit stack size, the current stack size. If it is, then we're good to go. Otherwise, we need to grow the frame and grow the stack. So in order to grow the stack, what basically happens is I basically check to see if the frame size plus the frame grow size is less than the frame limit. If so, then I reallocate basically by taking the current size, adding it to the grow size, and that's it. And then I just add the memory. Otherwise, if it's not equal, if the frame size isn't equal to the frame limit, I set the frame size equal to the limit and reallocate all the way up to the frame limit. And that's it, and then I just add the memory. For stack, it's the same story, but it's... okay, sorry, I was thinking of a bug that I could have had, but that's not a thing. So when it comes to growing the stack, it's kind of similar, but it's a little different. So we check to see the stack size plus the required size is less than the stack limit. The required size is going to be based off of how much we need the stack to grow. So if we go up to our example here, we need a total of 5 locals to, actually allocate this stack. So we can pass in, 5 here, and then we're going to basically check to see if, it's the amount that we need is less than the grow size. If so, then I set it to the grow size. Otherwise, I set the required size plus the grow size. So if we smacked up to the limit of the stack here, we're going to, since it's less than the limit of 250 or 512, then we're just going to allocate an additional 512 slots in the stack. Otherwise, we just, create a buffer of 512 on top of whatever we need. And then we basically just, get the current stack pointer index and the frame pointer index. The reason why you want to do this is because the stack pointer and frame pointer are now pointing to invalid memory because we're reallocating this data stack field, and these 2 fields are pointing to the pointer of data stack field. And as you know, when you reallocate a pointer, that pointer is going to move somewhere else. So at least that's my understanding. So this memory is going to be invalid. So we want to just get the index of where it's pointing on the stack and then just reset the pointer value of data stack plus whatever the index is later on. And then we get the pointer index by for looping through the entire stack and figuring out, what the pointer is. If you guys remember, we use pointer to access data in the actual stack. So it holds a myriad of, it could be stack data, it could be static data or whatever. Pointer is just a very important piece of item. So we want to make sure that all the memory is valid, so we just reallocate, and that's it. And then we just update the variables and we add the memory. Same thing here. Now this is if the stack plus the required size was less than the stack limit. Otherwise, if it's not equal to the stack limit, then we just update it to the actual limit, and that's pretty much it. Same code on either side. The only difference is that I'm using stack limit instead of, stack size plus required size. So same stuff there. And then, so once you have all of that, let's see if there's any more functions that we need to go over. So done delay. Let's see, bind, safe start. Oh, we actually haven't done delay. So when it comes to delaying, the way that it works is you say you want to delay for X amount of milliseconds. I only do milliseconds. I don't do microseconds because it's just my decision. So basically, the way that I do it is you pass in the amount of microseconds you want to delay or milliseconds you want to delay, and whether or not we want to increment the program counter. Um, yeah. Basically, what this does is this is a way for us to, when we actually delay, there's a problem, right? So let's see. If I scroll up here, I go to delay. So let's say we have this delay function. This is actually in the standard library. So if we call this delay function, this is going to call the system interrupt relative to the delay function. We need to increment the program counter after this to delay, because what's literally going to happen is we're going to execute this instruction, and once we come out of the function, we're going to check to see, oh, we actually need to context switch. So we're going to bounce, we're going to initiate the context switch, which means we're stuck at this instruction. So you're going to effectively be delaying indefinitely because we need to jump to the return instruction. So what we do is we pass in whether or not we need to increment the PC, and there's reasons why we do and we don't. And if so, then we basically increment it to return and then delay, so that way when we come back in, we just call return and then we keep executing. Now, when it comes to this, we enable the context switching on the thread, and then we try to context switch. Now, this is where it gets into the thread being the authoritative figure. You like, just because the scheduler tells you to context switch, you can tell it to screw off, because basically you might not be able to. So let's see. So let's just kind of go through it. So we check to see if we're already context switching, which is a new Boolean that I added here. We also have waiting and stack rebuild and relative frame. So add those and last microseconds. All of these are new fields. Everything else is the same crap that we've already gone over. Bound fibers as well. That's a new one. But everything else is the same. So, oh, we also have these two. Fiber, this fiber, last fiber, and next fiber. But once you have all that, then let's see. So there's certain criteria where it could, we can't context switch. We say, if the current fiber is null, the current call stack is null, or if we're inside of a native function, we return false. Now, I should probably wrap this in this, then do this. So we say next fiber is equal to null. Yeah. So basically what happens is if we're inside of a native function, here's where we could not context switch. Let's say we're at main, right? We're at the main function. The main function then calls foo. Foo then calls a native function called, I don't know, native cout or something, right? So this is a native function. Now we're inside of C++, right? Then let's say this native function then calls a high-level function of print. So the native function then calls back up to the high level. Now what actually ended up happening is we have what's called a native function inside of the call stack of the actual programming language. And that, this is a system that we have no control over. Once we call into C++, that is outside of our environment, right? So you can't really do anything about that. You can't context switch or force a context switch, because the C++ doesn't know about any of that crap. It doesn't know about the garbage collector. It doesn't know about the threading system. It doesn't care about any of that stuff. But now that we've put ourselves back at the high level, we have, visibility of all that, but we know that we have this native function inside the call stack, so we just say no thanks. So this will only work if, the current function was a native function and we tried the context switch on there, on that actual function. Otherwise, if we, have this scenario where we call into a native function and then back up to the high level, that's also not going to work. So let's see that example. So we for loop through the entire call stack, we get the frame out, we check to see if the function is JIT, and it's a native function, which means, again, native cout. If so, we can't context switch because this is outside of our environment. So we block it. So we basically just disable the signal of context switch and we return false. After that, we increment. So if we wanted to increment the program counter, this is where that program counter increment comes in handy. Then we, increment it. Then we set the relative frame equal to 0 and context switching to true. Now, what is relative frame? Relative frame is how we actually build the stack back up again. So we have, what is this, 1, 2, 3, 4 functions. So we have all these functions, right? Now, let's see how we would go about rebuilding the stack. So when it comes to rebuilding the stack, we're going to use what's called the relative frame. The relative frame is going to have us keep track of where we are in the call stack. So once we're ready to context switch, we don't actually return from this print function. We can't, because this may still have some work to do inside of that function. So what we do is we do what's called a soft return, where we basically just return out of it, but we don't actually shift back the stack. So we'll see how I do that in a second. But we basically shift this all the way back to the first item, and then we bounce back out into the main function. So if I go here, interpreter thread start. So this is the main function of every single thread in the programming language. If you guys remember, if I scroll down here, we try to execute a method with the main method address. Once we execute that method, this takes us on this call stack where we're physically calling functions to actually execute all this code. Well, what we're going to do is we're going to return back without actually manipulating the internal stack of the programming language. And then we're going to come back to this function. Then we're going to jump down here where we have a bunch of logic, which I'll get into in a second. It's actually quite a lot of logic, where we basically just try to look for the next context switch. So we call wait for context switch. We basically wait for the next function. Then once we come back to this coroutine, we need to rebuild the stack by setting the relative frame to 0, then 1, then 2, then 3. So as we call all of these functions, we're going to be comparing the current relative frame value to the actual calls value, which is going to be in the fiber. So in the fiber, we have this calls variable, which represents how many functions nested deep are we currently in the call stack. And in order for us to know that we're at the topmost function, we need to compare the relative frame in the thread to the calls variable. Now, because this is a thread-based situation where a thread is context switching, that's why this relative frame is not inside of the fiber object, because it doesn't make sense to be, right? Each fiber has their own call stack. Each fiber has their own program counter and all their own states and stuff. So to abstract that out, we keep that in the thread so that way we can properly, rebuild these stacks. So that's kind of how it works. So if I go back to, okay, so let's just kind of see like what the actual process would be. So if I go to execute, I go to system interrupt. I execute the delay command that we just saw, right? I check to see if we have a signal. Now, you guys know what that is. We literally just check to see. Now here, we check to see if we have a signal, and if so, if context switching is true, we return out of the function. And that's the soft return that I was talking about. So if we see that we're context switching, we literally just return out of the function without actually calling the return method that, if I go here, we have this return method function, which is what gets called when functions actually return from the programming language. Now we have a secondary. Now this is where the magic happens. So we have context switch check. And basically this allows this single thing right here, this single line, is the main and only way how coroutines work in the programming language. Without this, none of this stuff works. So basically the way it works is if we're context switching, or if we have a context switch signal and we try to context switch and get a positive, we get true returned, we just call return from the function, and that's it. That's all we do. We just return from the function, and that's basically how it works. Now, I want to mention you don't want to litter this context switch check all over the place. You want to put it in spots that are going to happen often enough that you can adequately context switch the programming language in a timely manner, but you don't want to put it in so many spots where you could get some nasty race conditions. So where I put context switch check is I put it in BRH, which is just go to basically. If not equal to, if equal to for if statements. Jump, which is another version, another subset of the go to execution. The difference is that this one takes a hard value. BRH takes a dynamic value from a register, so that's the difference. One's dynamic, one's static. That's why I have two. Also, when you call a function, so if you remember, we can call just-in-time compiled functions. So what if inside the just-in-time compiled function, we see that we need to context switch? We're going to soft return out of that function. We're not going to call the function epilogue. We're not going to execute everything in the epilogue. So what we do is, if I go to, where is it at? Function epilogue. Here it is. So you can see I have the label end of function, which represents the end of the function. I get the thread point and I actually return from the method. But then I have another label called function epilogue. This is what actually gets used when it comes time to return or soft return from the actual system when I see that I need to context switch. So that way I don't actually return from the function. So I just, re-update the stack. So that's kind of how that works. And then, so if I go back to thread.cpp, the spots where I do it is calling a function, like I said. If I scroll down, invoking a delegate function, jumping, jump not equal to, and jump if equal to, and that's it. Just a few spots. These are like basically the jump instructions and the call instructions and the interrupt instruction basically signifies the only time that we're going to context switch the programming language is when we call a function, when we run an if statement, or when we run a for loop or some type of control flow in the programming language. Once once that kind of happens, then that's basically it. Then we have, we actually do the context switch. So we just return back out, and that's pretty much it. So once we do that, once we kind of, have that system in place, we need to put the final piece to this puzzle, and this is pretty much everything. So if I go to system interrupt, interp, so interpret the thread start. Once we return out of the function for the first time, I've done something different. I have this initial setup. The initial setup is a Boolean inside this function that gets set one time, that sets the current state of the thread to running. It sets the attached thread of the current fiber and the state of the fiber. Now in setup, we actually do something different. So again, if you guys remember, you need both the fiber and the thread to run this entire system. So every time you create a thread, each thread has to have at least one fiber to run that thread. So once the thread actually executes, I call make fiber on that actual thread, and I set this fiber to the current fiber. Now the this fiber variable represents the current fiber that that thread is executing, or the current coroutine that that thread is executing at any given point in time. And I bind that coroutine to this current thread. So that way, I know that the thread at least has one coroutine that's running on that thread, and that's bound to it. So, there's that, and that's pretty much it. So after the initial setup, after setting everything up, we execute the function, and then once we return out of here due to a context switch, we skip this if statement. And I'm just going to go through the flow of how this works, because otherwise if I try to explain it's going to take too long. What we do is I say thread that this fiber, so I check to see if we have a current fiber or coroutine that we're executing. And if the current coroutine is bound to the current thread, or actually no, if it's not bound to the current thread, and there's an exception, I just print out the exception. And I think we've gone over this before. This function is actually called in the exit function. So whenever we exit a thread, so go to exit, we call print exception if there's an exception. And we've already gone over this when I went over my threading system. So I don't have to go over that again. But what this basically shows is, if you guys remember in my previous video, I mentioned that if a thread or if a coroutine crashes on a thread that it isn't bound to, that it's not going to actually crash the thread itself. It's just going to, print out the exception to the console and just keep executing from there. But if it is bound to the thread, then it will actually crash the thread. So what's going to happen is I'm going to say, now, let's say we do have an exception and we are bound to the thread. Well, yes, we have a fiber. The bound thread is in fact equal to this. So this if statement will be skipped. We'll come down here, the thread is not killed, but we have an exception. So we'll skip over this if statement, and then we'll skip over this catch statement here. We'll come down here, we'll kill the bound fibers, and then we'll exit, and then that's when we get the printout. So that's how it works, right? So if you have a fiber or a coroutine that crashed on the thread, then and is bound to it, then that's how the flow works for when it crashes. Now, if we don't have an exception, under normal circumstances, here's how we actually context switch to another coroutine. So we call wait for context switch. What that does, I have a bunch of coroutine debugging stuff. Guys, please feel free to put debugging information in your system. I don't go over mine because it's just kind of messy, but it's good to always have some debugging information in there, just kind of see what's going on under the hood. You can just kind of flick it on and off. I'm actually, it's kind of funny, I have a God mode, I know I'm going off topic, but I have this God mode feature in mine, and I recommend you do this too, where you can basically enable a couple of define statements, which will then unlock certain things in the programming language, so you can see different statistics and other stuff. But anyway, back to waiting for a context switch. So what we do, when it comes time to context switch from one fiber or one coroutine to another, the way it works is we set the current coroutine we're executing, and we set the attached thread to null. So now we're no longer attached to that coroutine. We check to see if the current coroutine is finished. If so, because we don't always get to this wait for context switch function just because we context switch. Maybe the coroutine is finished executing. Maybe it's just returned out of the main method. That's entirely possible. So if that is the case, if the coroutine is finished, we check to see if we have more than one bound fiber. If we only have one bound fiber, then we want to check to see if the current fiber's bound thread is not equal to this. So, if either of these values are true, so if the current thread has more than one bound fiber, or the current bounded thread is not equal to this, then we set the state to killed. You don't want to set the current fiber that we're executing state to killed, because we literally just set the attached thread to false. If you guys remember, the scheduler is going to kill any fibers that where we basically don't have an attached thread and they're killed. So the scheduler will free up that memory, and we don't want that to happen. So we only do it if we have other fibers to execute, or if we're not bound to that fiber or bound to that thread. Otherwise, what we do is we say waiting is equal to false, and then I just return. So what happens is, if basically what this means is the current fiber that is finished is the last fiber that is bound to this thread. So we return out of here, and that is right here. So we're right here executing. We call this function. We check to see if the state is equal to killed, or if we have the signal to kill, we jump to the end. Otherwise, we check to see if the fibers that we have left on this thread by getting the bound fiber count, which literally just accesses the thread's mutex and returns the bound fibers integer, which is updated by the fiber system. If the fibers left is 0, or the fibers left is 1, and the current fiber that we're executing is finished, and it's bound to this thread, then we say go to end. End is down here below this catch statement, where we literally just kill the bound fibers, which is, we only got 1, so we'll just kill that one, and then we'll exit the thread. And that's it. So that's kind of how that flow works if you execute the last coroutine. And then, after you do that, then we check to see if the state is running. So if the fiber's state, so if it's not finished, right? If the state of the fiber is running, which it's supposed to be, it should not be running, we set the state to suspended. And that's it. So we just, pass it this thread, and we set the state to suspended. I don't think I went over the set state function. The set state function, basically the way it works is, so we have, state. If it's running, we set the last ran micros to the current time since 1970, and we set the last, ran micros that way. So this way we can keep track of when was the last time that the thread was actually running, because the idea is that a thread can only execute one coroutine at a certain time. Doesn't matter how many times we context switch. The thread can physically only execute a single coroutine at a time. So we want to keep track of how long that thread has been running that coroutine with this last ran micros. So that's how the scheduling system knows that we passed the time of our time slice. And then, so if it's suspended, I check to see if there's a delay. So there's a sorry, I'm shooting ice. There's a delay function that has a default value of -1. That's why there's nothing here. Sorry, my voice is really dry. I've been talking for a while. If the delay value is greater than 0, we set the delay time equal to the current time plus the delay. So we'll see in a second how we actually execute or choose which is the next coroutine to execute, because it's a pretty interesting system. It's very simple, but it's also very smart. So we'll see that in a sec. Otherwise, we set the delay time to -1. We set the state equal to the new state, which is suspended. If it's killed, we unbind the thread, because obviously if you kill a fiber, it doesn't need to be bound to anything because it's dead. But we don't set attached thread equal to null, because we want the thread itself to willfully do that, so that way we know for sure that the thread is actually not running that coroutine. Because if you guys remember, we have to inspect the state of the coroutine to make sure that as we're channeling back through the call stack, we need to check to see if we're actually needing to context switch. So if it's killed, we set the state, we set finish to true, we set the delay time to -1, and stale fibers to, we increment it. And this is how the system knows, the scheduler system, to free up another fiber, because now we have a stale fiber. Otherwise, it just will never free up anything because there's no fibers to free. All right, so if we go back to here, I'm going to put this over here because it's a bit easier to see. Now here's how the actual true magic happens when it comes to choosing which coroutine to run next. So I have a concept of last fiber, and what this basically does is I have a fair system in terms of executing fibers or coroutines. So let's say I create a coroutine list, right? Let's say we have a bunch of coroutines here, right? Let's say we have all these are the coroutines that our system is currently running. And let's say it's running on a single thread, just to make things easy to understand. So we have, what is this, 1, 2, 3, 4, 5, 6, 7. So we have a total of 7 coroutines. Obviously, we're going to start with the first coroutine. So I'm going to put the star here. This is the current coroutine that we're executing. Once we finish executing and we're ready to context switch, this is going to be set to the last fiber. So I'm going to use this symbol as the last fiber. Now, what we're going to do is we're going to get the next fiber, and we're going to pass the last fiber that we executed in the list, so that way we can basically check it from then on out. So what we're doing is we're saying, all right, we just executed this fiber. I don't really want to execute that one again because that wouldn't be fair, right? You have to execute all these other fibers. So we're going to start from this point forward. So we're going to skip this one, start from here, going this way. And then once we execute this one, right, this one will be known as the last fiber. And again, we start from here, going forward. And then we keep doing that all the way till we get to the end of the list. Now, I know you're thinking, well, what happens when we get to the end of the list? What happens is the system knows that, so we'll see it in the function. We'll see that we're at the end of the list. Then what will happen is we'll just wrap back around to the front, and the last fiber will be set to null, I think. And then we'll just start here, execute this one. Again, last fiber, start from here. So we basically guarantee that we're for looping through the entire list and wrapping around constantly, so every single coroutine always gets executed. So that's very important. You want to make sure you implement that. But let's see. So what you do is you set the last fiber here to the current fiber that we're executing. Then we set the current fiber we're executing to null. Then we set that we say that we're waiting. We're a thread that's waiting. We set stack rebuild to true, which is used by the low-level system of the JIT, if you guys remember earlier on in the video. Then we set the relative frame to 0. Finally, I check to see if the next fiber is not equal to null. And if it isn't, and we'll see in a second when it comes to locking, that's the final thing that we have to go over, and then this will pretty much be it. But we assign the next fiber equal to the last fiber. So the next fiber that we need to execute, we're going to pass in the starting index. We're going to check to see if the last fiber is not equal to null. If so, we access the item index of that fiber. Now, where does this item index get set? This item index gets set when we add a fiber. So if you remember, when we add a fiber, if we find a spot inside this list, we set the index of that fiber on that list to the current index of where it is. Otherwise, if it's at the end of the list, we set the item index to the end of the list. So that's how we know where the fiber is in the actual list. Once we do that, then we basically, so we have this, we pass an index in, otherwise we pass -1, and then we pass in a thread. Now let's look at the next fiber. So here's where we pick which coroutine to run next. So we say starting index and the thread we want to run on. So we have starting fiber. Just do that because it's not really necessary. So we have the current fiber and then the starting fiber. And then we get the current log time one time. And I have certain criteria for picking it. So we check to see if the starting index is greater than 0, right? And if the starting index +1 is less than the data size. Because remember, we want to execute the next item after the last fiber. So starting index, which is the index of this, +1, which is this, if that's less than the list, then we can execute all of those. So we have that, and then once we do that, we for loop through from the starting index all the way to the end of the list, and then we get that fiber and we check to see if the fiber is not finished and the fiber is runnable. Now, the criteria to decide whether or not a fiber is runnable is it can't be suspended, it has to be wakeable, and the fiber's bound thread has to be equal to the current thread that we're executing, or the bound thread has to be null. We can't just run anything, because if a fiber is bound to another thread and we execute that, you're going to have a bug that I fixed that you want to watch out for, which I call hyper concurrency, where you basically have the same coroutine executing simultaneously on two different threads, and that is extremely bad. You'll get some pretty disgusting bugs if you end up getting that happening. So you want to make sure that if you're going to run this coroutine, either it has to be bound to the current thread you're executing, or it's not bound to any thread whatsoever. Now, then when it comes to locking, if a fiber is locking, we'll see when this gets set in a second, we pass it one time. So we just skip over it once, because, you might have a list of like 1 million coroutines, so you don't want to skip over it like 4 times. You just want to skip over it once. I could maybe increase it to 2 or 3, but you don't want to skip over a coroutine more than 3 times during, when you're actually like looking for a coroutine to run. And basically what happens is, if the passes is greater than the max passes, we set it to 0. Otherwise, we basically increment the max passes and continue. So we skip to the next coroutine, because obviously we want to skip over any coroutines that are locking, because that's going to be a blocking call and it's literally going to do nothing. So then we check the delay time. So this is how we call delay on a coroutine, and we honor that delay. So if delay time is greater than 0, and the log time, or the time that we started searching for the next coroutine to run, is less than the actual delay time. If you remember, when we set the delay time, it's the current time plus whatever the delay is. Then we basically continue from there. Otherwise, we return the fiber because now it's time to execute it. So if we've gone through all this crap and it's runnable, it's not finished, it's not locking, or if it is, if we've already passed it, even though it is locking, and we can run it because the delay time has passed, or it's not delaying at all, then we can run the fiber. Otherwise, we set the size equal to the starting index, and that's kind of weird. Basically, you want to go for the size. I don't know why I'm doing that, but basically, you once you do all of that, then you set the size based off of where you want to stop. So the idea is that you want to go so. This was the last fiber. You want to check all of these, and then once you get to the end of the list, you want to bounce back around and check all of these except for the current fiber. So that's kind of the idea behind it. So once you do all of that, then you basically just for loop all the way up until the index wrapped around from the previous value of where it was, and then you check the same crap. You just do the same stuff here, and if all that criteria matches, now the difference is that in this case I don't care whether or not it's locking. So once we get to the end of the list, where is it at? So once we reach the end of the last fiber, when we wrap back around, I just pick any fiber that's available, even if it's a locking fiber. So it's a less picky way of choosing which fiber to run. But this only happens one time. This only happens once we reach the end of the list. So it's always picky until the last item, and then it just picks whatever's available, because obviously we couldn't find anything because we're at the end of the list. And once we do all of that, you want to make sure you yield as well, because that you're going to be running this by a lot of threads. You return fiber, otherwise you just return null, and that's pretty much it. So that's pretty much everything for how the system works. And then so if I go back, so there's a few other things. So once we have the next fiber that we want to execute based on the last fiber's index, there's a potential that we could get null here, right? So while the next fiber is null, we yield to another thread, we sleep for 100 microseconds, and then we basically check the state of the thread. So have we been killed? Do we need to suspend ourselves because of a garbage collection? And then we get the next fiber, and we just basically keep trying until there's another fiber to execute. And we always start at the last fiber's index. So we just keep doing that, and we just stay at that point and just keep searching and wrapping around until we find a fiber. So this way, we always execute the next fiber after, or at least try to execute the next fiber after the current one that we're executing, or that we just executed. And then once we finally have a fiber, we guard the mutex, we try to, we set the context switch to false. We set context switching to false. We do what's called a safe start, and this is my protection against the hyper-threading bug. So if you guys remember, I mentioned it a few minutes ago where you could have a situation where you have two threads executing the same coroutine at the same time. Because theoretically, you could have two threads trying to get the next fiber, and they both pick the exact same fiber at the exact same time. It's entirely possible, and especially if you have like a big list of coroutines, it's even more likely with a higher list. Then basically what Safe Start does is it gains access to the mutex of the actual coroutine itself, or the fiber itself. So each fiber comes with its own mutex. So you want to access that, you want to check the state. So if it's suspended, it's not attached to a single thread, and it's not bound to a thread, or the thread that it's bound to is equal to the current thread that we're executing. So it's just a double check, basically, to make sure that we absolutely can execute this. We set the attached thread, and we set the state to running. And because we have the mutex, only one thread is going to be able to set this data at a single time. And then we return true, otherwise we return false. And if safe start is returned true, then we know that we can safely start and run this coroutine. So we basically set this fiber to the next fiber. We set next fiber to null. We set this fiber that we're executing to the JIT context to the current fiber. Otherwise, if we didn't start it, we set next fiber to null, and we go to wait, which means we go back up to the top and keep looping forever until this is done. And that's pretty much it. So once we do that, we bounce out of here, we come back to the thread or to the virtual machine. Let's see, so we go to, where's that? So we do this, we go to retry. So we come down here, it's not killed, we don't have an exception, we context switched, it's not dead. We have a fiber to execute, so we say go to retry, which goes back up to the top. We skip the initial setup, come down here, set registers based on the current fiber's registers, because registers is a thread local that we use for every single thread to access the registers for the current fiber. And then we, basically check to see what we need to do. So if the fiber is running and it's not finished, then we execute it. So again, I'm just being absolutely sure that we can execute this by checking the state multiple times. And then basically, if the calls is -1, which means we haven't executed this coroutine before, then we basically call it for the first time. Otherwise, we call shift to next method. Now, I'm not going to go over this because this is just a standard call to the function, but I will go over, now we need to rebuild the stack. So now we've gone through everything. This is the entire system. This is the last part of the system, where how do you rebuild the stack once you context switched and returned all the functions. So we call shift to next method, thread, pass it the thread, we pass it whether or not it's a native shift. What a native shift means is basically we need to call this execute function. Now, there's a potential that we could call, so let's say we have main, right? This main function was called by the execute. This is a function that hasn't been converted to the level. Then let's say we have the foo function. That is a low-level function. Then let's say we have, I don't know, print, which is not a low-level function. And then let's say we also have print chars, because that is used by the print function. And this is also not a low-level function that hasn't been converted by the compiler yet. What's going to happen is we basically call this function, we call execute here, then we call into the function natively, then we call execute again, but this time we don't need to call execute again because this is also not a function that is basically, it's not a low-level function, basically. So, these can both run in the execute function without having to call it multiple times. It's just a way to save stack space because, it's just a better way of doing it. So what we do is if it's a native shift, we basically get the current calls and we use the relative frame and we check to see if we've built up to the function. So if you remember, relative frame is going to be 0, 1, 2, and then finally 3. So if relative frame is 0, that means it's not equal to calls. We need to figure out, we just basically pull the data off the call stack and we check to see if the current function that we're executing is a JIT function. If so, then we return the JIT function. We set the caller of the JIT context, and then we set the starting PC to 0. We don't need to actually, I just do this just to make sure that the code doesn't actually jump to a starting PC, but this doesn't really matter. You don't really have to add that there. I return the actual JIT function, and that's it. After that, though, if it is equal to call, so once we get to the last one, what I do is I set the stack rebuild to false. I set function equal to the current function of the fiber that we're executing, and based on whether or not it's a JIT function, I return the JIT function. Otherwise, if you have a native shift, then I call execute and return null pointer. Same thing down here. It's the same stuff, just copy and pasted. And basically what this allows you to do is once we call it to execute, we then need to rebuild the stack again. So if we're still rebuilding the stack, meaning, we're here, we're at main, right? So the flow is going to be, we call main, we call into here, because this is a function that hasn't been converted to the low level. This, then it's going to need to call, or it's going to check stack rebuild. Now, at this current point, the relative calls, or whatever the function was, relative stack, I don't remember what the name of the field was, because I'm getting pretty tired. But relative fields, or whatever, once we know, like once we actually check to see if we're building a stack, and then we come into here, we're going to check the value, relative frame. So we're going to check the value of relative frame again. So now it's 1, but this time this is a native function. So we're going to return the native function, and then if we have a JIT function to execute, we'll call into that JIT function, and that JIT function will then also check if we're rebuilding the stack, call this function again, and since we're calling from a native function, we need to say native shift, which will then call back into the execute function again, because both of these two functions are high-level functions. So that's kind of how it works. I know it's really, really confusing. And I'm trying like really hard. I'm definitely gonna go to sleep after this, but basically once we do that, then that's pretty much it. And that's how the stack is rebuilt. That's everything. So this is the entire coroutine system. Hopefully it wasn't too complicated for you guys. Finally, also too, another thing that I didn't go over is how do coroutines lock. Man, this stream is terrible. It keeps going in and out. But basically, if I go to, where's that? It is in, I'm just going to go look for the lock instruction. So when we call the lock instruction, You basically call monitor lock, and this is like the last thing. Then I'm going to head to bed. Sorry about that. So when we try to lock it, this is I did modify this function. The only thing I did to modify it is, oh, my throat is really dry. um, I have a lock check mutex, and I check to see if the current fiber is equal to the if the mutex that we're trying to lock is equal to the current fiber that we're executing. If so, this means that we own the mutex. And I basically set the locking to false. I set it to true here once we call into this function. And you want to make sure that locking is not a blocking call. So basically, once a coroutine tries to lock an object, if it needs to context switch, it will context switch. Unlike other languages like Kotlin, locking is not a blocking call in my programming language. And it makes for some really insane performance gains because now you can execute a lot more coroutines that are locking all these mutexes, and you don't have like all this stuttering going on because they're all working together to make sure that everything gets executed. But if so, then I just increase the lock count. I set the thread that we're on. I set the locking to false on the fiber, and that's it. once once we if the current fiber that we're trying to lock or the current mutex is not equal to the current fiber, then I basically just try to lock it. And if we need to suspend ourselves, I suspend. Yeah, I'm gonna need to like close the stream in like a few minutes. If we're context switching, or if we have a context switch signal and we don't have an exception, and we try to context switch and it returns true, I return false. And what that does is, instead of actually jumping to the next instruction, I just return out of the function. Because we don't want to jump to the next instruction, we want to come back to this instruction and try to lock the object again because we needed to context switch. Now here's where the magic happens when it comes to locking, and this is why I'm able to, send data through channels and have all these mutex locks working together on thousands of coroutines. The way I do it is, wait, actually, did I actually skip it? Oh, okay. I guess that I removed that. Okay. Well, never mind that. But yeah, so basically, once you, I guess I removed it. I forgot that I changed this function like yesterday. Once you've been locking for like a millisecond, you're going to eventually have to context switch. So we're going to context switch and skip this coroutine because it's locking, and we know that most likely it's going to continue locking an object. So, we have all this information at the low level, so we can strategically pick which coroutine to execute. And of course, if we need to kill the thread, then we kill the thread, and that's it. Let's see. And then, once we come out of here, so once the coroutine or the fiber is not equal to, or is equal to -1 on the mutex, I try to acquire the lock to that by checking to see if the mutex is still equal to -1. And only a single thread at a time is going to come in here. And if so, then I set locking to false. I set the fiber ID that this mutex is owned by. And then I set the thread also that the fiber is executing on to the thread ID. And then finally, the locked count, how many times it's been locked, I increase that as well. Otherwise, if we come in here and some other thread had access to it before us, we release the lock and we go back to lock object, and we keep locking until we get a context switch, and that's it. So that is everything. I've gone through pretty much an end-to-end of the entire coroutine system. It's really complicated. So hopefully I answered you guys' questions, or you know, I know threading is a pretty interesting topic, so hopefully this gave you a pretty good insight into how multi-threading works at the low level, and how some of these major programming languages actually handle context switching. So that's going to be it for today, guys. My throat is killing me right now. I am going to head straight to bed. It's pretty late where I am. So hope you guys enjoyed the video. um, yeah, I'm just going to go to bed. So hope you guys enjoyed the video. Thanks for those of you who kind of popped in and popped out. I saw quite a couple of you coming in and out every now and then. So until next time, I'll see you guys later.